Assalamu alaikum and welcome to Aflak channel. Every year there are 2 days when the sun is directly overhead in Mecca. At no time in Mecca on these 2 days, anyone who sees the sun at these times can determine the direction of Qibla using the direction of the sun and the shadow. But are these the only times the sun is in the same direction of Qibla? In fact, no. By the end of this episode, you will have a way to determine the time of day when the sun is in the direction of Qibla or opposite to it in any location on earth. And as we are used in this series, each episode will be available in 2 versions, one in Arabic and one in English. This English version comes with English subtitles, and you can use YouTube's automatic translation feature to choose subtitles in dozens of languages supported by YouTube. Let's get started. This is the 6th episode in the series explaining the equations for calculating prayer times. In previous episodes, we calculated all prayer times in addition to sunrise time. We also learned one of the methods for calculating prayer times in areas where the sun does not rise or does not set, or when twilight does not disappear. And in this episode, we'll learn how to determine the direction of Qibla from any location on earth. And then we will learn how to determine the time of day when the sun is facing or opposite to Qibla. If this is the earth, the blue dot M represents Mecca, which is the Qibla direction, and the red dot P represents the location of the observer we want to determine the direction of Qibla for. To determine the direction of Qibla, we first need to draw a great circle connecting the location and Mecca, because the shortest distance between P and M is always part of a great circle connecting P and M. And by a great circle we mean a circle that divides the earth in half, and its center is the center of earth. And the shortest distance between the 2 points is part of this great circle. And this is the direction of Qibla. And it's the angle from the North Pole to the observer location to Mecca. But how can we calculate the direction of Qibla? If this is the North Pole, we have an arc between the observer location and the North Pole. This line represents the direction of north relative to the observer. We place another arc between the North Pole and Mecca. We then have a spherical triangle. We will always have a spherical triangle regardless of the location of P, meaning if the latitude changes to a location north or south, or the longitude changes to a location east or west. And this angle is the direction of Qibla. We notice that the angle is sometimes measured clockwise and sometimes counterclockwise, and the angle ranges from minus 180 degrees to plus 180 degrees. However, there is a consensus that we should not use Qibla angle because it is sometimes negative and sometimes positive. The common method for determining Qibla is what is called Qibla azimuth, which is the angle from the north in a clockwise direction, meaning towards the east. And this angle ranges between 0 and 360. It does not have negative values. We can easily convert between the 2 angles by adding 360 and then taking the remainder by 360. This way we can eliminate negative values. If we go back to the Excel file we created in the previous episodes, which contains the times of all the prayers in addition to sunrise time, if we change the location, latitude, and longitude, the prayer times are calculated according to the new location. Now we will calculate Qibla azimuth. First, we'll open a new sheet. We'll call it Qibla. Here we will enter Qibla direction Q, and the equation is mod A tan 2 sine of latitude of Mecca 21.4225 converted to radians multiplied by cosine of latitude converted to radians minus cosine of latitude of Mecca 21.4225 converted to radians multiplied by sine latitude converted to radians multiplied by cosine longitude of Mecca 39.8262 minus longitude converted to radians, comma, cosine of latitude of Mecca 21.4225 converted to radians multiplied by sine the difference in longitude of Mecca 39.8262 minus the longitude, all converted to radians, and then all converted to degrees, and we add 360, 360. And we see that this is Qibla azimuth in the location we specified. Let's call this Q for Qibla. Here we will calculate the opposite direction of Qibla because we'll need it later for comparison. The equation is MOD of Q plus 180, 360. Now we want to draw an arrow for the direction of Qibla because an arrow is much easier to view than angles. Here we'll put the number 0. Here we'll put sine of Q converted to radians. Here we'll put 0. And here we'll put cosine of Q converted to radians. Now we'll select these 4 cells. Then we'll go to Insert, click on this arrow to open the charts, choose All Charts, then select XY Scatter, then this type. Now we will remove the title, choose the line, go to the last option, Format, and then choose the ending type to arrow, and choose the size to the largest size, and then make the line wider. Then select the horizontal axis, go to Axis Options, set the minimum to -1, maximum to 1, major to 2, go to Labels and select None. We'll repeat the same steps for the vertical axis, minimum -1, +1, major 2, and labels None. Make the drawing a square. Now we'll choose the square in the middle and make it as large as possible. Right-click on the line and choose Data Labels, Add Labels, Add, then choose Labels, go to Options, we choose Value from Cell, then we choose Qibla Angle. Delete the Y value and choose a larger size. Now we'll choose the drawing and then choose Cut, go to the main sheet and choose Paste. Let's resize it and place it here. Now let's add some colors. We just want it to look better. Now if we change the location, the drawing will show Qibla direction, and the angle is always measured from the north in a clockwise direction. Now we have finished the easy step, which is determining Qibla direction using the equation. If we return to this drawing, we know that this is Qibla direction. We know also that if the sun is perpendicular to Mecca, we can determine Qibla direction using the sun because the sun will be towards Qibla. So all you need to do is make the shadow exactly behind you and you will be facing Qibla. But this is not the only situation. In fact, if the sun is perpendicular to this place, it's also in the direction of Qibla. Also when the sun is perpendicular to this place. And in both cases the sun will be in the direction of Qibla. Even if the sun is perpendicular to this point, Qibla can be determined using the sun. In this case, Qibla direction will be opposite to the sun. That is, you place your shadow in front of you and your face will be facing Qibla. In fact, anytime the sun is perpendicular to any point on this great circle, it's either the direction of Qibla or opposite to it. But how do we know when the sun is perpendicular to this great circle? In previous episodes, we calculated the sun declination, and from it we can know the orbit on which the sun is perpendicular on any day of the year. And the yellow circle here represents the points the sun is perpendicular to in a specific day. And sun declination changes from north to south during the year. Now anytime the yellow circle intersects with the great circle of Qibla, the points of intersection between the two circles are the times when the sun is either in the direction of Qibla or opposite to it. In most cases, the two circles intersect at 2 points. Each of these 2 points can be either in the direction of Qibla or opposite to it. If we also place a circle to show night and day, the half where the blue dot is located represents the day, and the other half represents the night. We see that the points of intersection can be either at day or night at the observer location. And of course, when it's night, the sun cannot be seen. But if it's in the day, we can use the sun to determine Qibla direction. There are also cases where there is no intersection between the two circles. However, in cases where there are 2 points of intersection, how do we know these 2 points? In fact, solving this problem was somewhat difficult because the equations were long and complex. While solving this equation, a quadratic equation emerged. We will not go into how to derive the solution because it requires a long explanation, but we will jump straight to the solution. So if we go back to Excel, first we need to know the sun declination, DEC, and we'll take it from the calculation sheet and we will name this cell DEC for declination. Here we will put Y, and here we'll write the equation, and I apologize in advance, the equation is long, but we only need to do it once. And the equation is minus 2 multiplied by minus sine latitude converted to radians multiplied by tan Q converted to radians multiplied by cosine latitude converted to radians multiplied by tan Q converted to radians multiplied by sine declination converted to radians plus 2 multiplied by minus sine latitude converted to radians multiplied by tan Q converted to radians multiplied by cosine latitude converted to radians multiplied by tan Q converted to radians multiplied by sine declination converted to radians, all raised to the power 2, minus 4 multiplied by 1 plus minus sine latitude converted to radians multiplied by tan Q converted to radians raised to the power 2 multiplied by cosine latitude converted to radians multiplied by tan Q converted to radians multiplied by sine declination converted to radians raised to the power 2 minus cosine declination converted to radians raised to the power 2 all raised to the power 0.5 divided by 2 multiplied by 1 plus minus sine latitude converted to radians multiplied by tan Q converted to radians raised to the power 2. This gives us the first dimension y. Now we need to find the value of x, and the equation is minus sine latitude converted to radians multiplied by tan of q converted to radians multiplied by y plus cosine latitude converted to radians multiplied by tan q converted to radians multiplied by sine declination converted to radians. Now we have y and x, we can determine the angle A, and the equation is a tan 2 of y comma x converted to degrees. And now we'll define t, converting the angle to time as a difference from noon time, and the equation is noon time, we take it from the calc sheet, minus angle divided by 360. We will put a dollar sign here because we will use it again. Then we use the time format. And this is the time of the first intersection point. Here we will determine whether the time is at night or day, Tn. And the equation is if absolute value of the angle is less than, we go to the calc sheet to the sunrise and we take the angle n, comma 1, comma minus 1. The number 1 means day and minus 1 means night. And let's add a dollar sign here because we'll use it again. Now let's change the format here. This is not required, but it looks much better. Select conditional formatting, select icon sets, select the colored circles, select conditional formatting again, select manage rules at the bottom, select edit rule, then select show icon only so we don't have the value. We'll change all the fields to numbers here and here, then change the number to 5, 0, and 0, and press OK. Here a yellow circle will appear representing the sun if it's daytime, and a black circle representing darkness if it's nighttime. Now we need to specify whether it's in the direction of Qibla or opposite to it. We'll define D, and the equation is sine of 180 minus Q multiplied by sine of the angle. The number 1 means the sun is in the direction of Qibla, and the number minus 1 means the opposite direction of Qibla. I will also change the format here, and again this is not required but it looks better. We'll select conditional formatting, select icons, select arrows, select conditional formatting again, Then select Manage Rule at the bottom, select Edit Rule, select Show Icon Only, change all the fields to numbers, and here, then change the numbers to 0 and 0. Here we'll see a green arrow pointing up if the sun is facing Qibla, and a red arrow pointing down if the sun is facing the opposite direction of Qibla. And now we have completed the first intersection point between the two circles. To find the second solution, we need to copy this row, then paste it here. Now we need to modify the first cell, Y. We change the plus sign to minus sign, and that's the only change. And now we have the 2 times of the intersection points. And we're done with the equations, and it's time to verify the calculations. Let's go to the main sheet. If we try the city of Riyadh, for example, latitude 24.7, longitude 46.7, we notice Qibla angle is 243.99. Now we go to Qibla sheet. We see that there are 2 times. One is at 12 night, and the sun cannot be seen, of course. And the second is 17:06:20. Let's go to Stellarium. Determine the location 24.7 north, longitude east 46.7. Let's change the date, the year 2025, month 1, day 1, time 17 hours, 6 minutes and 20 seconds. And here we see that the sun angle is approximately 243.99, which is the Qibla direction. We also see that this happens a little before sunset, and the sun is almost on the horizon. And sun declination is 22.95 south. If we go to the model we used at the beginning of this episode and put latitude 24.7, longitude 46.7, and put the declination minus 22.95, we see the 2 points of intersection. One is almost opposite to observer location, which is almost midnight, and the second is when the sun at the edge of the circle that separates night and day, and the sun is setting. So we have this model, Stellarium and Excel giving us the same results. Now let's change the location to latitude 33, for example, longitude 7. We see that when the sun's declination is 15 degrees north, there are 2 intersection points, both during the day. One in the direction of Qibla and the other is opposite to it. If we return to Excel, set the location to latitude 33, longitude 7. We see the direction of Qibla 103.35. Sun declination is close to 15 at the beginning of May. So we change the date to month 5, day 1, 2025. If we go to Qibla sheet, we'll see that there are 2 times. The first is in the morning at 11:33:41. Now we go to Stellarium and we set the location, latitude 33, longitude 7. We change the date to month 5, day 1. We set the time to 11:33:41. We know the sun angle is 103, which is the Qibla angle. Now let's return to Excel. We know the second time the sun is opposite to Qibla. The opposite direction of Qibla is approximately 283.4, and the second time is 20:32:49. Note that I did not change the time zone, neither here nor in Stellarium. Let's go back to Stellarium, set the time to 20:32 minutes 49 seconds, and we see the sun angle 283.4, which is the opposite direction of Qibla. Here we can also see that there are cases where both points are facing Mecca. If we take latitude 15, for example, longitude 75, we see that when the sun's declination is 20 degrees north, both points are facing Qibla, and both are during the day. Let's try this in Excel. Latitude 15, longitude 75, and we see that the direction of Qibla is 286.2. The sun declination is close to 20 on May 20th. So let's change the date to month 5, day 20, year 2025. If we go to Qibla sheet, we see the 2 times are 11:29:26 and 14:50:11. Let's go to Stellarium, change the location, latitude 15, longitude 75. Let's change the date to 20th, and we go to the first time, 11:29:26. we see that the sun azimuth is 286.2, which is in the direction of Qibla. Let's change to the second time, 14, 50, 11 seconds. We see that the sun azimuth is also 286.2, which is the direction of Qibla. Of course, there are cases where the two circles do not intersect, and there is no intersection points here. For example, if the declination is minus 23.44, which is the winter solstice, we'll see that there is no intersection points. If we go to Excel and change the date to winter solstice, 12/22/2025, we'll go to Qibla sheet and we'll see that times cannot be calculated because the two circles do not intersect. There are also times when all the intersection points are at night, like this case, and we cannot use this method. But in most locations and days, there is a time when the sun is either in the direction of Qibla or opposite to it during daytime. This method has two advantages. The first is that we don't have to wait for the two specific times on two specific days of the year when the sun is directly overhead in Mecca, because we can use this method in many days during the year. The second advantage of this method, which is more important, is that this method can be used even in places where it's night time when the sun is directly overhead Mecca. For example, if we take Auckland in New Zealand, latitude -37, longitude 175, we see that when the sun declination is 21.4, which is the latitude of Mecca, on the day when the sun is directly over Mecca, it's night time in New Zealand. However, there are times of the year when the sun declination is -20, for example. The intersection points are during the day. If we return to Excel, put the coordinates of Auckland, latitude -37, longitude 175, time zone 11, we see the direction of Qibla is 260.85. The sun declination is 20 degrees south on the date month 1, day 20. We see that at 8:22:48, the sun is opposite to Qibla, meaning 80.8. In Stellarium, we change the latitude to south 37, longitude to 175, and time difference to +11. We change the date to January 20th, and the time to 8:22:48 seconds. We see that the sun azimuth is 80.8, which is the opposite to Qibla direction. The second time is 16:38:54, which is in the same direction of Qibla, 260.8. In Stellarium, we change the time to 16:38:54. We see the sun direction is 260.8, which is the direction of Qibla. Of course, this does not apply only to New Zealand, but any place on earth, including the areas where the sun being perpendicular to Mecca cannot be seen, including North America, Canada, South America, or anywhere else in the world. If there are any additions or corrections to this episode, I will add them to the description below. I hope this episode was useful. Please subscribe, share the episode with those interested, and enable notifications. Thank you and keep safe.